All right, let's get started. Today's lecture is going to be about, always happens. All right, today's lecture is going to be about matrices and vectors and linear algebra. Before I start, let me, so the basic outline is going to be, we're going to talk, give you a second. All right. We're going to talk today about matrices and vectors, and the thing I want to emphasize today actually is there's really kind of a double view. Everyone's still talking. All right, we're going to start now. All right, we're going to talk today about matrices and vectors, and the thing I want to emphasize today, in addition to some sort of basics of linear algebra, is that there really are two different views of matrices that are very common in data science. There's sort of the more array-centric view as in terms of a way to store information, and then there's the linear algebra view, which is as sort of a mathematical object for actually performing algorithms. We're going to try to cover both of those, but be fairly brief with this. I mean, we're not, linear algebra is the language of a lot of the algorithms we use, but we don't want to spend too much time on it because frankly, it's pretty simple linear algebra that we're going to use later down the road. Then I'll talk on this lecture about the NumPy library. That's the main library that we'll use for both the array and the linear algebra view of matrices actually. And we'll finish up with sparse matrices. This is a topic in particular that actually is hugely important in any practical data science. Very, very often the objects you'll deal with are inherently sparse, and it's going to be very hard to deal with them densely. But it's for some reason one that seems to be taught less in a lot of machine learning and data analysis courses. Okay, before I start, a few quick announcements. So some comments about homework 1. So there's two comments I want to make. The first is that in the XML parser, the parser is updated for the website, for the latest version of the 2016 website, but there was one spot where I think we actually didn't update it, which was the total count for the XML nodes in the test case result. That is wrong. It's kind of actually obviously wrong because it doesn't match the number of open close tags you have, so it couldn't possibly be right. So just know that one's off. The open close tag should be right, but that one is off. We could fix it, but at this point, frankly, it's pretty late. People have been submitting to AutoLab and getting full credit without checking that, obviously. So just know that one's off. The rest are updated from the site. The second thing was that as people emailed us in this sort of very worried about the fact that if you look at one of the examples we give about an exception that should be thrown, there's a little bit of a traceback that has some of our solution code in it. This actually, we sort of knew about this. It wasn't a big deal. It's 2 lines in a very long solution, or a few lines in a very long solution. If you see that and want to use that, that's fine. I wouldn't recommend trying to decipher our solution from like a little bit of a few lines of code from traceback in our execution. It does emphasize one thing though, which is that you can of course add other attributes to the class if you want to. You do not have to just have those attributes. We will not test for any of the other attributes of the ones that we specify, but you can add whatever you want to the class. I mean, you can certainly add anything you want to that class to make it work. So those are just 2 things. Those are sort of 2 comments I've seen coming up a lot. Other than that, I think there are certainly common themes about certain tests people don't pass, but I think they're mainly being handled well in the office hours or on Piazza. So if there are other things that you think really have not been addressed, I'm trying to sort of read everything and respond to a small amount, but read everything and kind of get a sense of what are the big problems. And other than these, I think people are kind of working through most of the issues. So. Okay, next thing about switching sections. I got a few comments about this. So I tried to actually do this a little bit more organized way. In the past, we've somehow been able to, but this year we were basically told that we cannot do anything other than just have people fill out course section switch or add drop forms. So what you have to do is there's a link on the website now. On the website in the frequently asked questions section, there's a link to the relevant form. Download that if you want to switch sections. That means if you want to go from 688 to 388 or vice versa, or if you want to switch between the A and B sections of the 688 course, download that form, fill it out. We will be very quick to respond back to it and give you a signed copy of it back. You'll have to get other signatures as well then, but there shouldn't be any issue with getting them. We've done this a lot of times for the other courses, and so it should all sort of go fine. But you do have to go through that kind of somewhat annoying process, but it's just sort of a pain that because before the add drop deadline, there's too much, there's enough flexibility in the wait list, and then after it, you have to fill out this form. So unfortunately, everyone hopefully is in the course that wants to be in the course. For switching, you have to just bear with us, but we'll be fast to respond to them. Homework 1 is due Wednesday night at midnight on Wednesday. Remember that there's a maximum of 2 late days allowed for the assignment. That means that Friday at midnight is the absolute latest time you can submit anything. After that, you will get no credit because we're going to release the solutions post some stats with the solutions on Friday. So, or on Saturday rather. So after that, so it's much more important to submit something and get some credit than it is to fine tune your solutions locally and get no credit. And don't put it till Friday. Even if you're going to use the late days, for the same reason that you shouldn't put it till the last day if you're going to submit on time, don't leave it till Friday. And finally, homework 2 will be released this Wednesday at midnight as well. Any questions about the logistics side of things? All right, let's jump right in then to matrices and vectors. So, as I said before, vectors and matrices are kind of they're sort of some of the core data structures we use, but also mathematical objects we use in data science. I personally write almost every algorithmic work I do in matrix form. It's just sort of the language of machine learning. It's the language of how we write these algorithms out. Now, of course, in this class, we're not going to get too detailed in sort of the most advanced possible algorithms when it comes to machine learning and things like this. But it's really important to kind of speak this language, to speak the language of matrices and vectors in order to kind of understand what these things are doing. And frankly, I've always found that writing things in matrix notation actually simplifies a lot of things. When you write a matrix vector product, as opposed to an expression with a big sum and a lot of sums, one after the other, it's much more intuitive to me to just look at these things as actual matrix expressions, and hopefully, that's the emphasis that I want to put here, is that the hope of all this is to make the notation simpler, not harder. And if you're finding it harder, then it probably means that you want to review some of the more basic principles of vectors and matrices. So a vector at its core is really a 1D array of values, right, or a 1D collection of values. And we're going to write it as x is in this bold script r, or Blackboard script r to the n, to denote the fact that x is an n-dimensional vector. So that means it has n different components. And they all have real valued entries. That's what that R means. It means it's just real valued entries. Now, if we want to write it out, we can write it out as x equals the collection of all the elements in x. And xi here, x subscript I, will refer to the ith element of the ith entry of the vector x. But this is now in the language of linear algebra, but if for those that might have sort of seen this before, by default we're going to consider vectors to represent what are called column vectors. So it is a matrix essentially with many rows but only one column. And if we want to represent the opposite, which is called a row vector, we'll use the notation x transpose. The transpose flips the rows and columns of a matrix, and so for a vector we'll think of the transpose as transforming a row vector to a column vector to a row vector. Hopefully people have seen this a little bit before. If not, even if you don't have that much background in linear algebra. All right, now a matrix is just the 2D extension of this, right? A matrix is a 2D array of values. And we're going to use the notation A being in R to the m by n to denote a matrix with m rows and n columns. Right? So m is the number of rows, and n is the number of columns here. And the entries in A are denoted A subscript ij to denote the entry in the ith row and the jth column. That ordering is very important, right? So especially because it doesn't always correspond to how they're stored in memory on a computer. We'll get to that in a second. But it's very important that the first entry here is always the row, the second entry is always the column. So if you sort of list the entries of the matrix A, they look like this, right? So 2, 1 there would be the second row in the first column, etc. Now, this will do a little bit less, but if we want to refer to something, I'll try to do this as much as I can to be consistent here. If we want to refer to only the ith row, we'll kind of use NumPy-like notation even in math form, in that we'll say ai colon, which will mean just the ith row. So the row is always I. So if I say 2 colon, that would mean the vector that represents this whole second row here. In contrast, if I said I colon j, that would be referring to column j. So I colon 2 would be this column here, right? In both cases, they sort of mean those columns or rows as a vector. And sometimes we'll use other notation too. So it's depending on the case. So sometimes we'll only be referring to columns of A, for example, and then I might just go ahead and drop the colon there. But I'll try to be consistent about telling you before I ever do that. And for this class, I'll try not to do that because this maps pretty well to the actual notation you'll use in NumPy that it's worth me to just try to stick with that as much as I possibly can. Question, yeah?
When we refer to ai colon, are we getting row vectors in there?
Yeah, that's a great question. So the question was, when we refer to ai colon, do you mean a row vector or do you mean a column vector? It hopefully won't matter, and I'll hopefully just specify it when I say that. People mean both. I will usually mean a column vector because the vectors are always column vectors unless you specify it that way. But it isn't always the case, and it's worth, because also NumPy has weird notation where it doesn't differentiate between a row vector and a column vector. I'm not going to actually be strict about what I define there because it can kind of depend on the situation. Okay, now this is the main point that I actually wanted to convey at the beginning here, and I want to just emphasize it again, is that matrices really are two things in data science, right? In the first sense, they're the most obvious way to represent tabular data. And as we talked about before, tabular data really is one of the most fundamental kind of types of data we're going to encounter in data science, right? And the obvious way to store it. So we'll talk about it in a second, but if you have a table, especially a table with only real valued entries, it's kind of obvious to store it as a matrix. And secondly, they're also, though, the foundation of linear algebra, right? So they're also this mathematical construct where we can sort of do things like perform operations, form inverses, cancel equations, stuff like this, right? And they're really a language for talking about operating on and manipulating systems of linear equations. And these are actually two very different views, right? One is kind of almost a data structure view, right? Sort of, how do you represent a big table of data points? And the second one is, how do we represent and reason about systems of linear equations? And both of these, though, I will say, are very important in the context of data science. The first very much in the context of kind of data management and managing the data, and the second one in the context of algorithms and how we actually process data. And so understanding both those perspectives is really crucial for virtually all the data science you're going to do. All right, so let me just sort of say the obvious thing here, right? Is that let's take the view about matrices as arrays, as representing tabular data. So let's look at the grades table that we had in our database lecture. And let's ignore the primary key for a second. That was the person ID. Let's ignore that one because that's actually not that's sort of the key of the table, maybe not quite the data. You could put it there. It doesn't really matter, but I'll just ignore that for now. So if we're going to represent this data, the data in the table, ignoring the key for a second, it would be very natural to store this in a matrix of size 3 by 2, 3 rows and 2 columns, right? Because obviously, that's what the data looks like in the table format, right? We have just a bunch of numbers in our table. These represent the grades. And we want to store them sort of in a matrix that actually captures that same form, that same layout. Now, that seems very obvious, right? What more could there be to say about that, really? But from a data storage standpoint, there actually is one subtle issue here that I want to address, which is how this data is actually stored in memory. And the odd thing here is that there's more than one convention for how to do this, and they're both widely used in actual numerical methods. So the question is, computers fundamentally, they access memory as a big linear structure, right? They sort of memory is just a linear structure. And so when you have a data, when you have data like that, the obvious question is, do I represent this reading kind of row by row or column by column. Okay, because I have to lay out my memory, I have to lay out my data somehow linearly in memory. And do I represent it by row or by column? It turns out these are both very, very common to do. So the row ordering, what's called row major ordering, would lay these out by row. So we would sort of read things off row by row. So they'd be stored as 100, 80, 60, 80, 100, 100. And that's stored that way in memory. And the column major ordering would be the opposite here. It's you sort of read off the data by columns here. So you'd have 100, 60, 100, 80, 80, 100 would be how it's laid out in memory. And that might seem like a small sort of deal there, but it actually changes. This has sort of far-reaching consequences on how quickly you can access elements in this table, for example, especially because due to things like caching and locality of caching, how you store the data has a big effect on sort of how quickly you can access different types of or different slices of this kind of tabular data. Okay, and the other big thing is that there are these two standards are both extremely widely used in practice. It's not like one is never used and the other one is, is the only one that's ever used. These are both completely standard in different languages. So it's actually kind of a sort of interesting story. So what happened is that in the C language, the row major ordering became the standard, right? So if you make a multidimensional array in C or C++, and actually in NumPy has row ordering as the default, it will lay it out in row major format. So it'll sort of lay out the data by row, and that's how a two-dimensional array in C or derived languages will work. On the other hand, Fortran, which was for a very, very long time the standard language for numerical methods, has by default column major ordering. And so Fortran decided, and I think actually it sounds weird if you've only seen the row major ordering, because it just seems like, well, of course you'd be laid out like that. That's how memory is laid out. But if you think about vectors being by default column vectors, it actually can make a lot of sense from a mathematical standpoint to lay things out in column major ordering. And so Fortran decided, back in the day, to use column major ordering. And so what this means is that all this code that runs in the background that does all the operations we sort of care about actually operates on column major ordering, or column major order matrices. And so this causes a lot of issues, as you might imagine, when you have to interoperate between different languages and libraries. But just be aware that this exists, and this is not sort of a trivial issue. When you use these things, if you use some other numerical library, it will often assume a different format of your matrix than you are using. So just be very aware of that. All right, the last thing I'll say is sort of about higher dimensional matrices. I shouldn't call them matrices, actually, because there's another word for these. These are called tensors. That term has gotten a lot of traction recently, mainly because TensorFlow and these libraries ostensibly operate on tensors. But really, just as with matrices, there are really two perspectives on tensors. So on the one hand, tensors are just sort of the obvious extension to multi-dimensional arrays, right? A vector is a one-dimensional array. A matrix is a two-dimensional array. You can keep doing this and just form three-dimensional arrays and four-dimensional arrays, right? It isn't very complicated, actually. It's actually quite straightforward from a pure standpoint of data storage. You just have to figure out, the generalization of whatever the row major or column major format is. You have, rows and columns and whatever the third dimension is, depth of the thing, right? You have to figure out what order you do them. And you either do it, left to right or right to left in terms of the indexing. You don't ever have like the middle index be first and whatever. But and it actually is kind of nasty, honestly. How do you deal with even the layout of tensors sometimes in memory, especially when you want to manipulate them. But that's actually not that hard, right? This is just sort of the standard thing you would think of, where you have essentially, if I have multiple slices of this thing, I would just lay it out in memory by sort of stacking them up one after each other, and I can index into them using exactly what you would think, figuring out what row, column, or slice I'm in. That's all I want to say about that. The other thing I'll say is that there also is another linear algebra view of tensors, where tensors are sort of the multidimensional analog to linear operators, right? They are sort of multidimensional linear operators. For the most part, there isn't that much data science that uses the linear algebra view of tensors, I will say. There is some. So if you think about like tensor factorization, if you've heard these terms before, that is a more linear algebra view of tensors. So they're actually looking at tensors like linear operators, applied to matrix. Maybe they're operators that can manipulate matrices instead of like matrices manipulate vectors. But they're really relatively rare. That sort of use of tensors, at least in most data science. So the good news is you don't have to worry about, and it's actually really crazy too. Tensors, they have things like they have analogs of things like eigenvectors and eigenvalues, but they aren't unique. They don't always exist, and they're really kind of much nastier mathematical constructs. And so we aren't definitely not going to worry about any of that for this course here. We're going to largely, when we talk about tensors at all, we'll think of them largely just as multidimensional arrays. All right, any questions so far? I realized I just forgot to bring my paper here, but oh well, maybe I'll use the board if I need to. Because next we're going to talk a little bit about basics of linear algebra. And here we are going to give some sort of basic rules of linear algebra. And hopefully most people have seen this before, but if you haven't, I also have for previous courses, developed some material on kind of the basics of linear algebra. And I will put a link on the notes to that other material for those that want a review. Frankly, of much more than you're going to need for this course, but if people want that, there is a resource available. Okay, so the first thing I want to say here is that at its core level, matrices and vectors provide a way to express and analyze systems of linear equations. This is often, I think, forgotten in favor of just the definitions of matrix multiplication and matrix vector products and stuff like this. But really, linear algebra is about representing linear equations. So let's talk about this set of linear equations here. We have two equations and two unknown variables, x1 and x2. And here, our equations are 4x1 minus 5x2 equals a negative 13, and negative 2x1 plus x3 equals 9. Now, that gets cumbersome to write after a while. So if I had to write every expression I had, if I have 100 equations, 100 unknowns, writing it sort of term by term and specifying every single coefficient and every single element in the vector gets pretty cumbersome after a while. And so matrix notation was developed really to make that simpler, really to simplify how we talk and write about linear equations, sets of linear equations. So I can write that same exact set of equations as the expression ax equals b, where A is this matrix, so it has the coefficients of the first equation in its rows, and B has the right-hand side in its rows, in its elements. Right? And this is just shorthand for that. And in fact, everything that sort of comes from linear algebra, like why do we have a weird definition for multiplication? I mean, when you first see a matrix multiply, it's not obvious why they're doing it that way. And it all just follows from the fact that what we want to do is we want to talk about these types of linear equations. That's what it is defined as, and that's why you have matrix multiplication being some weird operation that involves sums and not just element-wise products of the two matrices. Okay, so having said that, there are some very basic operations that you should know about for linear algebra. The first one is just addition and subtraction. So if I take two matrices, A and B, they have to be the same size to add them. Right, so A and B are assumed to be the same size here. They're both going to be m by n matrices in our case here. M again is the number of rows, n is the number of columns, and their sum is just a new matrix C, where the ij element of C is just the ij element of A plus the ij element of B. So exactly what you would kind of think an operation should be, right? And addition and subtraction work that way. Okay, so very important though, matrices you're adding together have to be the same size, or subtracting has to be the same size. For A being m by n again, The next thing we're going to think about is the transpose operator. The transpose swaps the rows and columns of a matrix. So a matrix so this matrix here, its transpose, it's a square matrix, so the diagonal entries don't change, but the transpose would flip these two elements here. And just similarly, the transpose of a vector would result in a row vector instead of a column vector. Right? Where essentially, the formula is of course very simple. It's just saying that C would be, if A is m by n, then C is n by m. So it's of course, the sizes have to be flipped too, where the ji element of C is just equal to the ij element of A. The hard one here, the hard operation, which is not as intuitive the first time you see it, is matrix multiplication. So here we have two matrices, A and B, and they're different sizes. A is m by n, and B is n by p. And the crucial part here is that the number of columns in A is equal to the number of rows in B. Right? Their product, so the product A times B, is a new matrix C, which is m by p. In other words, we take the inner dimension n here, drop it, and the dimensions of C are the outer two dimensions, m by p. And the formula for this is that Cij is equal to the sum over some other index k going from 1 to n. Remember, n is the size of the missing, of the middle dimension here. Of this, the sum over this product of sum of these products of matrices. So Aik times Bkj. And what's sort of happening here, let's see, I have one more. I have one more slide. This will sort of specialize a few things. But what's happening here is that we're taking the ij entry of this thing is the inner product, what's called the inner product, or dot product sometimes, of the ith row of A and the jth column of B. Now, a few sort of useful properties. The matrix multiplication is associative, so you can do the multiplication in any order you want. By the way, that sort of property is what is basically what you can derive this expression from that property, and the definition of a matrix as a linear operator, like we defined it on the previous slide. And it's distributive in that if I have an operation like A times B plus C, I can separate this out as A plus B and A plus C. However, and this is very important to not make this mistake, it is not commutative. So the product A times B does not equal B times A. In fact, this doesn't even make sense as an operation, right? Because in order to multiply the matrices together, they have to have the same inner dimension, right? So it has to be, m by n and n by p. And if these have those sizes, and p is not equal to m, this would not even be a valid expression we could form. And even when it is a valid expression, say they're all n by n matrices, these are not the same. The actual result here of multiplication, following this definition, is going to be different in general. I mean, in very odd cases, it can be the same, but it's a very, very specialized case that it can be. So a lot of the intuitions we have and the manipulations we do for scalar products don't follow for linear algebra. You have to be very careful about what sort of intuitions you can carry over from the sort of normal math you're used to, and whether or not these apply to linear algebra. So just be very aware of that. These things are sort of very important to be aware of when you deal with linear algebra. But just know that these are very important to keep in mind. We're gonna have a poll on this in a second too, so get to that in a second. Okay. The next, I have two more slides on kind of properties, but the second to last slide on the properties of linear algebra deals with the matrix inverse. So this is actually as complicated as we're going to get when it comes to linear algebra in this class. I will occasionally mention the word eigenvector, especially next class we talk about the PageRank algorithm for graphs. I'll mention the fact that it's computing an eigenvector on graphs. That's useful to know, but you're not going to have to really know what eigenvectors are for matrices. But you should know what the inverse is. So the inverse is sort of defined in the following way. We can define what's called the identity matrix, which is a square n by n matrix that has ones on the diagonal and zeros everywhere else. And it's pretty easy to show that if you have a matrix A, which is m by n, then A times the identity on the right or A times the identity on the left, important, those are different sized identities. The one on the right has to be a n by n one. The one on the left has to be an m by n identity. But they both just equal A. Right? And that's actually very easy to show just from the definition of matrix multiplication. If you just sort of write it out, what happens when you multiply by a matrix with all ones on the diagonal and zeros everywhere else, you'll see that you just get your original matrix back. And so that is the identity matrix, the square matrix, ones on the diagonal, zeros everywhere else. Now for a square matrix, and not all square matrices, but we'll just assume for square matrix, we'll just assume these do exist for the most part. If you have a square matrix which is n by n, the matrix inverse, which we denote as A inverse, A to the negative 1, is the unique matrix such that when I multiply A by A inverse, or do it on the other side too, or A inverse multiplied by A, it equals the identity. So actually, this is an example of a matrix multiplied that does commute, but it's an unusual case. It doesn't happen very often. Right? And the value of this is that this matrix lets us solve systems of linear equations. So for example, we had our old system of linear equations a few slides ago. We said that we would write this system as AX equals B. So if I want to solve this system, in other words, if I want to find the X that actually satisfies this equation, what I can do is I can take this equation here and multiply on the left by the identity, by the inverse of A. Okay? Then A inverse times A will cancel out. It'll just be X. And so the solution you get for what X is that X equals A inverse times B. This is like the fundamental equation of linear algebra, right? Now this doesn't really say very much, right? Because we're just sort of, for any actual instantiation, I have not actually told you what the values are, what the solution is. But the nice thing about this is that as far as we're concerned, actually this is a solution. So if I give you a big system of linear equations, and I say, what's the solution? You can just write it in terms of the inverse, right? Because you can take that inverse and you can plug it in to NumPy or any other linear algebra library, and you can get the solution back, right? You don't have to worry about canceling rows and canceling columns, that stuff. That actually all happens underneath the hood when you compute the inverse, or actually more importantly, when you solve a set of linear equations like this. But the point for us is that this actually simplifies our life a lot, because writing out solutions explicitly for how you solve linear equations, we all did this in high school, right? We had to go through the algebra of canceling rows, multiplying them by one, subtracting one from the other, adding them together, and seeing what remains. Right? It's kind of tedious, and it's completely algorithmic, right? And we can ignore all of that and just write X equals A inverse B. Right? And as I said, because so much data science will use kind of the language of linear algebra to perform its operations and to perform the algorithms, this is a really useful sort of level of specificity to talk about when we talk about data science algorithms. Now, I should mention, sort of very importantly, a point which I will not highlight that much sort of in practice, but of course, these inverses do not need to exist for all matrices. So there can be matrices that doesn't matter what you multiply it by, you will never get the identity. And these have to do with conditions on things like the linear independence of the columns or rows of a matrix. We're not going to really consider too much. We'll talk about a few such possibilities later, but we're not really going to worry about this too much for our purposes, at least not right now. But just remember that when you think about inverses, you do want to think about whether they can exist or not. But when we get to that point, I'll discuss that point more, because I don't want to yet define kind of what the criteria are for an inverse actually existing. Okay, any questions so far? I know we had linear algebra as like a prerequisite for this course, or at least mentioning it, so hopefully this is a review for everyone. As I said, if not, I will include some links to linear algebra references in the notes. Okay, last slide. Just some miscellaneous definitions and properties, which may be useful. If you take a product of matrices and transpose them, that's equal to the transpose, to the product of the transposes. But you have to flip the order. So A times B transpose equals B transpose times A transpose. The same thing happens for inverses. A times B inverse equals B inverse A inverse. But you have to be very careful here, because for this to apply, both A and B have to be square. Remember, we actually only define the inverse for square matrices. So this expression is meaningless if A and B are not square. You cannot write A inverse for a non-square matrix. As something we're going to see again and again, and I write this so often that I almost sometimes forget that it's not obvious to, it's not just the most natural thing for everyone. So if you see me writing complex linear algebra and it doesn't quite make sense, you can't quite follow it, just stop me and we'll back up and we'll go through it. But it's so common that I just will write like this all the time. But this particular, if I have two vectors, x and y, that are both the same dimension, the matrix product, x transpose y, is called an inner product. And remember, y here is a column vector, x transpose, because it's a column vector transpose, is a row vector. So the resulting product is the product of a row vector and a column vector, i.e. it'll be just a scalar valued result. And it's just the sum over all the dimensions of the product of the two entries in those two vectors. People write this sometimes also with like angle brackets and stuff like that too, but I'm not going to do that. I think just this is the sort of the matrix form of it, so I'm just going to stick with that, and that's what I typically write. Okay. And it's so common that I do it all the time, and again, stop me if I think I'm covering everything here that I use later in the course, but I mean, not everything. We're going to talk a little bit about derivatives and stuff like that too later on. But that one I use so often that I wanted to make a special note of it. And then finally, the last thing I'll say is I do sometimes use this notation here, which is the Euclidean norm. And this just means the square root of the matrix interproducted with itself. So in other words, it's also the square root of the entries of the element, the entries of the vector squared, of the sum of squared entries. Okay, I think that's it for what I'm going to put you through in linear algebra so far. Again, it's worth spending some time just to get familiar with all this, because it really is the language that we use that we're going to use later to describe basically all our algorithms. Okay, so before now we get to sort of the nitty-gritty of NumPy, let me start a poll and talk about valid linear algebra expressions. So the question here is, here are some matrices, and nothing, as being someone that writes everything in linear algebra, nothing is more irksome than when people write an expression that does not actually syntactically compile in terms of linear algebra, right? So it's invalid. So the question here is, which of these expressions are valid linear algebra for those sized matrices? Forget about what they do, actually. Forget about sort of what they're actually accomplishing. Just, do they even parse as an expression? All right, let me open up the poll. Remember, check them if they are valid. Don't check them if they are not valid. Actually, maybe maybe sooner than that. All right, I'm going to close it now. 10 more, well, 10 more seconds. All right, let's close it. Again, if you didn't get in, just send us an email. Okay, let's the results here. All right, so, all right, people have some explaining to do. Okay, so the first one, let's what was the first? A plus B. Unfortunately, I don't have the, maybe I'll bring those up, but there was at least a majority for the correct answers here. But there is a share of too much weight, especially on those two. But let's go through them all in turn. Oh. Okay, first one. Why is or is that not a valid expression? Right, it's not, because A and B are different sizes. You cannot add them together if they're different sizes. These are both errors that will be thrown when you try to do this programmatically, and just errors if you try to write it as math. So don't make those errors. Second one, is that valid? Yeah, that's valid, because B times C is an n by n matrix. Remember, the middle dimensions drop out, and so you're adding an m by m, n by n, and an n by n matrix. Second one, is that a valid expression? Third one, is that a valid expression? Okay, that is not a valid expression because so you can form A times B there, but A times B is n by m, and I'm saying here that m is strictly bigger than n. So it's not a square matrix, so you can't invert it. Right. This one, is this a valid expression? Yeah, it is. There's even a little tricky thing here that would only actually technically be valid if m is bigger than n. Otherwise, you'll form a matrix that is not invertible, but that I'm going to gloss over for now. But just people might, if you've seen that before, just be aware of that. But that one is valid. If you look at the whole product there, you get an n by n matrix, and so that can be inverted. The fifth one, why is that not? Why not? Yeah, so CB is a valid product, but then X is n-dimensional. C times B is M by M, and X is n-dimensional. So you can't even form this product here, all right? And so B times X doesn't mean anything, and so that's not valid. And the last one, yeah, the last one's not valid either. You can't multiply. So this would be an m-dimensional vector, and this would be an n-dimensional vector. And you can't add those two together, okay? So be aware of these things. I know people may just be answering fast because the goal is to answer these things and get credit for attendance instead of not answer them. But for those that weren't quite sure about these things, it would be good to go back and kind of just look at those 4 slides of rules and really sort of understand them, because these things are going to creep up and get you if you are not familiar with linear algebra. Again, it is the language we use to write virtually all the algorithms you'll see in this class. Okay, so now let's talk about libraries for matrices and vectors. And the first thing I want to say here, and this is actually an interesting point that maybe people might not be that familiar with. The first thing I want to say is that linear algebra computations, first of all, they underlie virtually all machine learning and statistical algorithms, right? So any kind of deep learning method, any kind of, not even deep learning, but simple linear machine learning, they're all just based upon lots of linear algebra. And because of this, there have been massive, massive efforts to write really fast linear algebra libraries. And that might seem kind of counterintuitive because these things are so simple in some respects. For instance, suppose we want to have a C routine. I mean, we'll use C at least. We won't use Python for this. But suppose we want to implement a C routine that multiplies 2 matrices together. Right? What could be simpler? We already saw the algorithm. The algorithm is, you just do this. You have 3 for loops here. You set the ij entry of C to be equal to 0, and then you keep adding the corresponding AI, K, and BKJ elements to that sort of accumulator there. Right? That's the definition of the algorithm. What more could there be? So it turns out if you implement this in C, run it with all the optimizations on, it'll be about 10 times or more slower for large matrices than an actual linear algebra library will be. And the reason is this does not exploit the actual cache structure of the CPU at all. So good linear algebra libraries, which have been incredibly highly tuned to sort of be maximally efficient for the actual cache structure of CPUs, the memory hierarchy of a CPU, they basically do block operations. So they'll multiply matrices in block form. Well, they'll do little blocks at a time, not at all in this order, in very unintuitive orders. And they'll also be very well tuned for the exact size of caches on different CPUs. So Intel has one. It's called MKL. There's things called Open Blast or Goto Blast. There's really a lot of these. Atlas is another one. They're they're massive code bases for things as simple as matrix multiplication. So do not try to implement even very simple things yourself when it comes to linear algebra. You're always better off using a library. What that also means, by the way, is you should make sure that your installation, one of the reasons that I like to recommend people use Anaconda in Python is that it comes with a very nicely tuned NumPy library, which has as its backend a very nice fast linear algebra library. If you install your own version of NumPy, chances are it will be compiled with sort of a system installation of NumPy. It will not be optimized the way these other ones are. So just be aware of that. Your code might be 10 times slower than someone else's code just because you didn't install the right sort of version or the right backing of NumPy on your system. Which is why I like Anaconda, because it comes with all that kind of prepackaged. Okay, so let's introduce NumPy now. So NumPy is the standard library for matrices, vectors, and linear algebra in Python. Actually, I'll link to this, but there was an interesting blog post that I read a few months ago, basically arguing that the reason Python became dominant in data science is because of NumPy, and because, even more importantly, because of the way Python allowed for easy interaction with memory arrays. So NumPy all operates on memory arrays, and that ability to sort of do fast manipulation on arrays, I think, and I actually agree with the premise of this article, that essentially that allowed Python to take over, and is why it is so dominant right now. When Python came out, languages like Ruby were just as popular in a lot of ways. But for some reason, it did take off in data science, and I think this is actually one of the reasons. NumPy really is a reason for that. Okay, now NumPy provides, at some level, provides both a framework for the tabular array version of matrices, so storing multidimensional arrays, and it provides linear algebra routines. So it does both those two things. But it's important to note that NumPy, the sort of NumPy type, which is called an ND array, they really fundamentally are multidimensional arrays. So they can be, three. They can have 3 dimensions. They can have as many dimensions as you want. They are fundamentally multidimensional arrays. They just also have calls that let you operate on them like matrices and vectors. It's sort of a subtle point, but be aware of that. As I said before, and I actually probably should have just left it into this slide, there are these very specialized, man, I forgot to put the parentheses here. Oh well. Upgrades in the, let me just do it right now actually. Upgrades from the Python 3 to Python 2 to Python 3, even in the slides. Okay, quick fix. I'm going to capitalize it now, of course, because PowerPoint likes doing that. Of course, I want to capitalize everything when I put another parenthesis in. Okay, so the nice thing about NumPy, as I was saying before, is that there are these very highly tuned linear algebra libraries, and if you have a good version of NumPy, it will be backed by one of these. So these things are called BLAS, which is the general framework for the basic linear algebra subprograms, and LAPACK, which is for a slightly more advanced set of linear algebra routines. These were kind of general interfaces that were developed in, in the 70s, 80s, 90s for linear algebra routines, and then several people developed, they became kind of a standard interface for how you implement these algorithms, or how you implement the interface to these algorithms, and then there were very highly optimized versions of those libraries that were released. So these are things like Atlas, BLAS, or Intel MKL. I think actually my version, I assume most of those versions of Anaconda then would default to using Intel MKL. But they all work. Those, as long as you're using one of those things, you're in good shape. If you're using a system generic install of BLAS, it actually typically is not very well optimized, and so you don't want to do that. And your code actually could be 10 times slower for no reason, and you just didn't install the right version of NumPy. That's a big deal when you're doing data science, right? To have a 10 times slower thing. So make sure your NumPy library is up to date. And if you want to know, type this. mp_config.show. That'll tell you what libraries you're compiled against. You have to kind of, and then basically, I mean, you won't get that much out of it, but you can search to see, is there OpenBLAS, MKL, or any of those keywords in the output of that call. Okay, so I want to just give a few quick examples now of NumPy code. If people need it, I can actually run this in a notebook if people sort of want to, but I'll post the code also. So because we don't have a ton of time, I'm going to try to go through it just in terms of the slides. But if people have a point, maybe we can always switch to a notebook and kind of go through that. If people have one point of confusion, we can switch to that and go to a notebook. Okay, so let's talk first about how we go about creating NumPy arrays. So NumPy arrays, again, they're sort of 1D or 2D arrays. I can create a 1D array, i.e. a vector with saying b equals numpy.array, pass a list of numbers to it, and that will create then a 1D NumPy array. If I pass a list of lists, it will create a 2D array, i.e. something we can use as a matrix. I can also create sort of other things like ones or zeros or random numbers. And I can create matrices that are those size too. In a wonderful sort of idiosyncrasy here, when you say ones and zeros, you need to pass tuples of sizes. But when you call the random function, you don't pass a tuple of sizes. You pass just the sizes as a list. That's one thing that has always irked me, and I frequently make that mistake. So just be aware. Ones and zeros, the call requires parentheses, a tuple of sizes. Random does not. I can create an identity matrix by the I call, and I can create things like diagonal matrices by the diag call. This actually is a typo here. This should be random.randn. I realized when I tried to run that code. Okay, any questions so far? This is sort of general creation of matrices and vectors. Yeah?
For random, you need to give that
is the dimension of the variable. So it's not like between, it has nothing to do with the range. All the random calls specify the actual dimensions of the matrix you're getting back. So .random will return a 5-row, 4-column matrix, in this case, of Gaussian random variables. That's what this does. And rand in general is like that. It's never specifying the range or anything. It's always specifying the size of the matrix you want to create. Yeah?
Diagonal always from the top left to bottom right.
Yes, diagonal is top left to bottom right. The reason for that is, like the identity is, essentially, if you look at what a diagonal matrix does, it scales the rows or columns of the matrix, and that doesn't make any sense if it's, the other way around. It doesn't do that. Yeah? Rand n gives random Gaussian variables, so they are standard Gaussian. They have 0 mean and variance 1. Random.rand gives you uniform between 0 and 1, but in both cases they're continuous random variables, not integer random variables. If you want to select like a random integer, you can use np.choice as another thing that will like choose one of a subset, but those will by default always give you continuous random variables. Yeah. Yeah. Are they going to? Others will be 0. Yes. The question was, what does rand diag do? What I actually recommend is everyone just sort of execute this and see what the results are. So I have. Let's see. Let me just quickly switch to it for a second. This notebook is going to be. I will incorporate this with the notes like usual, which actually I'm trying to get up a little bit sooner this time around. But this is the creation of all these things. So you can create all of them, and then you can do things like print D, and you can see what it is, right? So I would just go through it. If you're curious about this thing, I would just sort of go through it and see what results you get. Question up there, yeah.
And 2D arrays, or can you have like an ND array of more than 2?
So the question was, can these all create ND arrays? Yes, they can all create ND arrays. I mean, actually, if I'm sort of typing. So we could do, right, and that would actually be a rank 3 array, a sort of tensor of 3 slices, each of which are 3 by 3 rows and 2 columns. Okay. All right. The next topic, which is actually, you do a lot of this in data science. So this is one that's actually good to, you're not going to digest everything here, but you, I actually realized there's also a typo on this one. Some of it didn't actually update. Hang on. Okay. Do that. Okay. So I had these. I just had IDX for those. Okay. So the next thing that sort of matters is how you index into elements of a NumPy array. And the nice thing here is that fortunately this is actually fairly intuitive in terms of it matches kind of the notation you use for linear algebra, or maybe vice versa. We try to make linear algebra notation in this class at least match this kind of notation. So the indexing that you use into arrays is a lot like what you did with lists in Python, right? So you can use things like index directly into an array, into the array there. Importantly, it's not, you don't say like A0 and then another bracket for the next one. You just would say A0, comma 0 selects the 0th entry of that matrix. In general, A open bracket I, comma j would select the element in the ith row in the jth column of the matrix. But you can also use the colon by itself to select the entire row or column. So this would select the entire 0th column of this matrix. Sorry, 0th row of the matrix. Yes, that should be row there. It should be the 0th row. So select the 0th row and all columns. And you can also do things like select parts of it with slice indexing. So the same with Python lists. You can say select rows 0 to 3. And just like with Python lists, that's not inclusive. So it will select the entries, the rows 0, 1, 2, and the column 1. You can also do sort of fancier indexing than this, though. So I can create another array with a bunch of integer indices and select one of my rows or columns here by a list or really an array of integers, rather than a slice or something like this. And there are two types of sort of indexing you can do in this form. You can first of all have a list of integers that will select sort of any set of the rows or columns by the integer index of that row or column. Or I can have an array of Boolean values that will sort of provide a mask of which rows to select or not select. Okay? So actually, these two things are doing the same thing. For an A, in this case, it has to be at least it has to have 5 rows here. It would select the 0, 1, and 2 rows of this matrix, and I guess here the third column. And here I specify that the 0, 1, 2 locations of this vector are all true, and the rest are false. And so that will actually return the same thing, those two. You can also do some fancy indexing on 2 different dimensions, but you have to be very careful here. So if I have something like this that sort of indexes into different sets, and you do something like this is actually not what you want. This will not give you a subset of rows and columns just like you think it will. This will actually give something else. And so if you want to first select these rows and then select these columns, you have to do this instead. Just be aware of that sometimes things don't quite do what you want. So when you get really fancy, so you should start to get a little bit fancy here. So things like Boolean indexing are really useful for selecting subsets of an array or a matrix. But if you get too fancy, things start to mess up. So be careful about being too fancy in terms of these things. The best way to learn this, by the way, is just to experiment with these things. You'll have the notebook that has all this code, and so you can just try out seeing what actually happens when you run these different things. Any questions on that? Yeah. Yes, it has to be a NumPy array. Sometimes it will be able to convert automatically, but if you provide a list, for example, it can sometimes convert that to an array, but just be safe and always pass it as an array. They're meant to be arrays, and if you're passing a list or something like that, it's effectively converting it to an array anyway, so just pass it as an array. I think one of them doesn't work, and one of them does work, but I don't even remember because I always just pass arrays. Okay, so basic operations on arrays, and 2D and 1D arrays here. So we're going to create a bunch of some random arrays here. Addition and subtraction, just what you would think. You just multiply, or sorry, you just are adding the elements or subtracting them. Here's the important point, though, is that multiplication and division of NumPy arrays are not matrix multiplication or matrix solves. They are just element-wise multiplication and division. So here I could write A times B. That is not a valid matrix product, but they're the same size. And so it's a valid product in NumPy. All right, so this is very, very important. This is not matrix multiplication. This is just multiplication of the individual entries. Similarly, this one's actually even trickier because this does something. A times x. That is not a matrix vector product. What that actually will do is that will actually multiply all the columns by x. So it'll scale all the columns in the array by the value in x. If I want to scale the rows, you don't do it the other way, though. That doesn't work like you might think. Because multiplication in NumPy can go either way here. So it doesn't actually work that way. So if I write A times x, it gives me the same thing. If I want to scale the rows, I actually write this weird expression here. Don't worry about that. This is something I actually don't really want to cover here. There's a lot of interesting what's called broadcasting rules that NumPy uses. When you multiply or add or do anything with 2 arrays that are different sizes, there's a whole suite of rules that it uses to determine what to actually do. And I can change the implicit size of these things by specifying none as some axes here. And so what this is doing is this is actually a broadcast rule that basically tells it to scale things by scale the rows rather than the columns. Don't worry about that one. Okay, I'm putting it there just to emphasize that weird things happen. When you start getting really good with NumPy, you can do some pretty amazing things with broadcasting, but it also can really mess you up if you're not familiar with it, especially because it will just work, and things will just work even though they're not what you mean to do, right? So when you get the sizes wrong, they will compile fine, everything will work fine, and it won't do what you want to do. So be very aware of that. Be very aware of sizes. Check your matrix sizes before you multiply matrices, before you do anything with matrices. There's a good chance something is just the wrong size that you're multiplying together. Another little fun thing that NumPy has is that this will transpose the matrix. It will just change rows and columns in the ordering. But this one does nothing. So NumPy has no notion of a row vector versus a column vector. A 1D array is just always just a vector. So transposing that just does not do anything. So again, if I want to do a transpose product, I have to be very careful about how I go about doing that. You have to be very aware of that. So you cannot always transcribe math notation into NumPy notation. Okay, so let's talk now about the linear algebra side of NumPy. And we'll start then with matrix multiplication. So this was actually introduced in Python 3. Before Python 3, you had to use a function called dot, np dot, or a dot b, or something like this. But fortunately, maybe, depending, I guess, on whether you like it or not, Python 3 introduced the at operator as a matrix product. So if I have a and c, that is now it's not a valid, I couldn't put a times c there because they're different sizes, and times is just element-wise multiplication in NumPy. But I can put a at c, which means a matrix multiplied by c. That's a matrix that would be 5 by 3. And it will return, of course, a 2D array. It also works for matrix vector products. So if one of them is a vector on this thing here, it will return a 1D array corresponding to that matrix vector product. And if they're both, oops, this should be a little x. I think it probably PowerPoint capitalized it again. This is if they're both 1D, it will return a scalar because it'll just return the inner product, which is just a scalar. Right, and notice that I'm not specifying a transpose there. I'm just specifying. Again, let me shrink the font here. I'm just specifying x matrix product z, and it ends up being a scalar product. So what this all means is that the kind of multiplication you do, whether it results in a matrix, a vector, or a scalar, depends on the size of the arrays here, which is very strange because if these happen to be matrices, if they're variables that happen to be matrices, it will return a matrix. If they're variables that happen to be vectors, it will return a scalar, not a NumPy, not a one by one vector. It will return just a scalar value. And so getting the returns from NumPy is actually something you have to be very, very sort of aware of and figure out the kinds of returns it's giving. And I'm sort of emphasizing that because you will encounter this a lot when you write any code that uses NumPy in Python. And things like transposes also are confusing. So here we need to multiply the transpose of a times y, and you can do it this way. You can do it this way. You can also do it this way, which is weird. But you can't do it this way. All right, so you can left multiply the transpose because transposing a vector doesn't do anything. And they wanted this one to work, I think. So they had to make this one work then. But this one here doesn't work because a and y are not, you can't form the product a times y because they're not the right sizes. So this one is definitely order dependent, so be very careful about that. Now, there's also this numpy.matrix class, which was supposed to solve everything here. It's supposed to just treat everything as real matrices, and it would, multiplication for a matrix class is actual multiplication. and everything's a vector. So row vectors are row vectors, column vectors are column vectors. And it was actually just a mess. That don't use this one. Interoperating between it and vectors is a total pain, or it and normal arrays is a total pain. Most functions will return arrays, not these things. So you're constantly sort of casting between the two types, and just don't do it. The one annoyance is when actually functions do return this. You have to cast them back to be arrays, but that's just get used to that sometimes. I would highly recommend against, again, if you want to, you can, but I'd highly recommend against using the matrix class in NumPy. All right, last slide about NumPy is solving linear equations. So we had our equation before, b and a. We had our, ax equals b, set up our equation. How do we go about finding x? Well, there's two ways you can sort of do this, or two ways you can think about doing this. I could form the inverse of a and multiply it by b, and that would give me x. Right? And I can form those inverses with the lineage.inverse of a function. In general, though, you do not want to call that function unless you have a very, very good reason for it. Instead, whenever I want to solve a set of linear equations, you should use the solve call. Lineage.solve, where you pass the matrix and then the right-hand side that you want to solve for. The reason is sort of a subtle one, but it has to do with how you actually compute that solution. So it turns out that actually from a sort of a pure, not big O notation, they're big O, both the same complexity, but from a standpoint of the actual number of operations you do, the constant term, computing the solution to a linear system is actually much more efficient than computing the inverse of a matrix. The way this works internally is you form a factorization called an LU factorization, then you use back substitution to actually find that, to find the solution. That is strictly cheaper than forming the inverse. So if you didn't sort of follow that, don't worry. Just remember that computationally, the solve call is much faster than actually forming an inverse. So don't form the inverse. Even if you think it maps more closely to sort of what you write or what you do in terms of the math, just don't make that call. Okay, any questions now? I have a whole section left, but I might actually push it to next time and address any questions if there are some here. We have that overflow lecture, so I want to make room for it if it'll make it more intelligible. And I don't want to give sparse matrices too short a shrift. Okay, so in that case, I will just preface sparse matrices, and we'll finish up with them next time. It won't take very long next time, but it's worth sort of emphasizing. Okay, so the basic idea here is that in practice, many matrices that we see in data science are sparse. If you have a matrix that indicates like a document/word matrix, word occurrence matrix, right? These documents have these words in them and they don't. If you have all the words in your entire universe and then all the documents in your universe, that matrix will probably be very sparse, right? It'll not every document has every word, and not every word occurs in every document. In fact, especially the ones that don't occur that often are the ones that are most interesting probably to that document, right? So this is going to be a sparse matrix. What this means is that many of the entries of this matrix will be 0. And it seems kind of wasteful to keep around a whole lot of zeros in memory if they're all just a bunch of zeros, right? Both in terms of computation and in terms of memory storage, right? This seems kind of wasteful. And it actually is very wasteful. Another great example is graphs, right? So if you represent a graph in terms of a matrix, you would sort of have an entry in the ijth element, say if there's a link from node I to node j, right? Actually, this is exactly how a lot of graph algorithms work. They work by encoding the graph in matrix form, called the adjacency matrix of the graph. Now again, unless your graph is dense, unless every node is connected to every other node, this is going to be a sparse matrix. There aren't not going to be that many connections. And in fact, it is exactly those sparse matrices that make large graphs possible. If they were just dense, it would be impossible to store or reason about them. So again, storing all these zeros is a huge waste, both in terms of computation and in terms of memory. We're just storing a bunch of memory that's just 0, 0, 0, 0, 0. And then if we want to do things like a multiplication, that's a little less obvious maybe, but it also seems reasonable. We're multiplying by 0 a whole lot. We know those are just going to cancel out. Why are we really doing that? So what sparse matrix libraries provide, they provide an efficient way of handling sparse matrices kind of natively, where you actually only represent in the matrix those entries that are non-zero. And they do it in different ways. But note one important thing is that this, from a standpoint, and this is a little bit misleading here, but the point I want to make is this is really more about kind of the storage and computation of matrices. From a standpoint of the math, these things are kind of the same, right? So A times B is the same formula mathematically, whether or not A is sparse or dense. It's just that from a storage standpoint, I can store a whole lot less memory if I exploit that fact. And maybe I can also exploit the fact in computation. If I know I'm multiplying by 0 a whole lot, maybe I can speed things up by exploiting the sparse structure of A. So what I'm going to do, and I think I'll do it next time because I think we'll get to it next class, is it actually fits very well with graph algorithms anyway, because graphs, again, are basically of this form. I'm going to go through how matrices are represented in sparse form. And it's not always the most, it's not maybe what you would think. People probably think of actually the first of these two, which are called coordinate format. That basically, again, I'll play in detail, but it basically encodes it as, a list of row, column, number entries, which seems very obvious. But actually, what the most efficient way of storing these things are something else called compressed sparse column format, which does something different. It actually only stores basically offsets the different columns in the matrix and then the indices of the rows within that column that have the non-zero entries. So we'll talk about why that's a good thing to do, and we'll talk about actually also how it relates to graphs next time when we start up next time. Okay, I think we'll end a few minutes early now.